Hi, my name is Steff Evans and I'm the lead FEA engineer at Evotech CAE Limited. This video, presented in collaboration with MSC Software, makes up a tutorial from the Apex 101 for Aerospace Applications series and is focused on a number of assembly management and modelling strategies within Apex. We're using the Harris Hawk Service Pack 1 release, highlighting key functionality using the model tree structure and associated tools. In this worked example, we'll go through the full model development for a typical aerospace assembly, in this case a fuselage frame structure with over 800 unique sub-assemblies and parts. This will be focused on a number of different assembly management and verification strategies. We'll also look at the concept of a model representation, which allows for the build and analysis of different fidelity models in a single Apex database. In this worked example, we'll go through a number of key stages. Stage 1. Model Assembly Definition. We'll demonstrate how complex CAD and model assemblies are imported, created, manipulated and viewed in Apex. Any parent-child entity, such as solids and mid-surfaces, respects the assembly architecture to allow ultra-fast manipulation for large models. Stage 2. Sub-model verification. We'll look at how a discrete part is defined within the assembly structure for model checking and verification. Resultant Solve uses computational part technology to integrate analysis output into full assembly level solution. Stage 3. Full assembly verification and analysis. We'll look at sub-assembly integration and solve performed at many levels within the product hierarchy. Connector technology such as glue contact allows full model assembly for ultra-fast verification, analysis and or export to external FEA technology. And then finally, stage 4, model representation. We'll look at discrete model representation such as a coarse loads and or a fine detailed joint definition, which allows models with different fidelity to be contained within a single Apex database. Results output can be also generated and assessed, which respects each model representation. Okay, so we'll get started with the model assembly definition within Apex and look at some imported geometry. So in the Apex environment, simply browse to the location of the geometry. We can bring in a single file or multiple files, in this case frame 11 step file, which contains all the model definition for the assembly that we wish to analyse. So turning the solids on into view, as it were, and we can see the full extent of the model. So we've got a typical aerospace thin-walled shell construction with lots of rivet, bolt and fastener detail in there, making up the full model definition. In the model browser tree we can see we've got over 800 unique sub-assemblies, so pretty complex large model. So we're going to use the information in the model browser tree. We're fortunate in the sense that the CAD definition has been generated very nicely with discrete names per entity or sub-assembly. So we're going to use the browser search function to pick out those entities and remove them from the structural assembly, as it were. So first of all, we're going to create a new assembly. We're calling it fasteners. So we're going to ultimately take out all of the redundant fastener definition for this first level model and just leave us with the structural entities. So based on the search string, so we've got lots of split pins first of all. So the split, using a split term within the search string, we can cut those entities out of the original assembly and then paste them into the fastener definition or fastener container subassembly to simplify the model. So we're going to repeat this. So we've now got rivets, so we can again highlight them with the search term, cut them out of the main structural assembly and then paste them into the fastener assembly, and we'll repeat that for the remaining fastener entities. We've got bolts and other fasteners in there which we can just cut out and move into the fastener assembly. So just a simple way of simplifying the overall sub-assembly. We can do this by picking from the user workspace from a display perspective. but because of the search terms and the way the CAD geometry is set up, the assembly set up, it's very straightforward to manipulate this geometry or the subassembly architecture into a manner that we can control nicely. So we're left with 64, I think, structural entities which make up the structural parts, so we can just cycle through those in the model browser tree. And if we change the color of the fastener assembly and then just look in the workspace, so we can see now we've got things like split pins, nuts, bolts and rivets all highlighted in red, and we can effectively remove those from the assembly architecture to make our modeling and analysis task much more straightforward. So we take those out of view, and then we just show the frame 11 assembly, which is going to become our structural target, or target for the structural model build, and we've got all of those structural components highlighted. So we can auto color each entity within the tree to give us a unique color per part or subassembly, and it's a very nice display, or simplified display in terms of what we've got with the overall definition. So looking at a particular part, so we can hover over that part and right click and use the option center in browser, and that will take us into the specific tree location to show that we've got a subassembly with a part underneath it and then a solid body contained within that. So we can interrogate that particular part. So in this case we're going to use some of the measurement tools to measure a fillet in this case, and we're going to use that for a subsequent, or use that dimension for a subsequent defeaturing operation, which we'll be performing on the full assembly. Remember, so we've taken out all the fasteners, so we're just effectively reducing the complexity of the model, or simplifying the model, and we can see how some of those fillets are controlled in the specific areas of each model. So once we've got an idea of the geometric dimension, we can defeature all of the subassemblies in one hit. So select the entities from the model view space, and then go into 3D fillets, and then we can see in the fringe on the right hand side that Apex has highlighted two sets of fillets, some coloured blue, some coloured green, so we can change the range dimension, changing that to make it more appropriate for what we want in terms of our defeaturing operation. And we're going to set a control with 7mm in the range, so any fillet larger than 7mm, such as those on the struts shown on the left hand side, will be maintained within the model, and then any features less than 7mm radius will be removed. So just highlighting those in orange, and then middle mouse button to accept, and Apex runs through, cleans up the geometry and removes all the defeatured, or rather defeatures all the fillets of less than that dimension chosen. So just going to get a little bit of time to perform the operation, and then we can come out of the defeature tool and see what we're left with in terms of the overall geometry. So zooming in, and we can see, yeah, for a couple of those regions the fillets have disappeared, and this again makes it a more simple operation in terms of our mid-surfacing, which we're about to perform. So we're going to use the mid-surface or single thickness solid with the auto assign thickness checkbox turned on. Perform the mid-surfacing operation. So Apex is creating the mid-surface and also the subsequent shell thickness property based on the original solid definition. So a very nice way of working quickly with the model, and we can see a fringe plot of the resultant thicknesses. We can turn off the solid and show the free edges. So these are the mid-surfaces that have been created, and each mid-surface is contained within the parent subassembly part where each solid was defined that was used for the underlying surface, or the underlying mid-surfacing operation. So we're just going to center it in browser, look at the discrete part definition, and then we're going to move the adjacent mid-surface that's created. So just looking around in the model browser tree for the adjacent paired surface, as it were. So just turning on a couple of parts to get the entity that's required. So there we go. So we've got the currently, so those surfaces, pink and green, are contained in two separate subassembly collectors. So we're going to copy and cut and paste the solid and the resultant mid-surface into a single subassembly. So you can see that by the fact that both entities are now the same colour and contained under that unique subassembly. And if we put the full assembly on, we can see how that manipulation has been defined within the full assembly. So measuring some of the hole geometry, so just getting the hole diameter 6.35 millimeters, and we're now going to defeature all of those surfaces to remove the 2D holes, again less than 6.35. So Apex has done a good job in highlighting the small and large holes. So we're going to leave the larger holes, and then all of the holes defined in blue in the fringe plot on the right hand side, simply select them and then middle mouse button to accept, and Apex will remove those from the resultant geometry. So again, another step towards cleaning up the geometry to give us the resultant target geometry for meshing. So once we've done that, we can surface meshing at 10mm element edge length with the auto meshing algorithm turned on, and just on a quick look we can see that's a relatively appropriate or reasonably appropriate element size for this type of structure. And then we can look at the element quality and show that we've got some areas of the model where we have poor element quality, such as the element quality check is showing that has failed. So we would not be able to run an analysis with such skewed or highly irregular elements. So it's a case of looking through the model and understanding where those poorly defined elements are, and usually it's a function of bad geometry or overextended mid-surfaces, that type of thing. So what we're going to do now is just look at one particular area of interest, again, so the green surfaces that we picked out earlier, and we can see if we center in the browser, so we've got under that part we have two solids, two surfaces and two unique meshes, and the red line between the interface between the two surfaces shows that they're not currently stitched together. So we're going to stitch them, and then we can see in the model browser tree we now have a single surface and a single mesh for that representation. Defeature on a manual basis now just to remove the hole, and we can see as we defeature the mesh updates, turning the element quality on, and now we can start to make some sense of this mesh geometry and mesh definition on the single part level. So following the defeaturing operation, we're just now going to use the vertex edge drag tool, so we can see the guidelines, and it's just simply a case of manipulating the geometry. The mesh automatically updates and the element quality automatically updates, so we've got almost a real-time feedback in terms of any model manipulation we make at this level. So again, very quick way of using the direct modeling geometry engine within Apex to get to where we want to be with the model topology very quickly. So we repeat that for the areas which are obvious, and then we can isolate and enhance any other areas. So basically that posts to screen only the failed elements and then the geometry which those elements belong to, and then we can again use the vertex edge drag. We can see that the mid-surfacing has just created a couple of extra vertices where the original fillets would have sat. If you remember, they were there before we defeatured, so it's just left some vertices behind. So we do that defeaturing operation. On the left hand side, the model browser tree shows that in terms of element quality we now have good, well, we have no invalid elements anywhere. We have some poor and bad elements, and we could take some time to understand where they are, but in terms of our loads level fidelity, we're perhaps not so concerned about local detail at this stage. We're just trying to get a mesh on the structure to allow us to understand the overall stiffness of the structure and load path. So checking the element normals and norm consistency, and then looking at the shell thickness. So if you remember from the mid-surfacing operation, we had auto thickness turned on, so the shell properties have been populated by that auto thickness parameter, and we can look at the solids overlaid over that resultant shell mesh definition. We see we've got a perfect definition in terms of the shell property to 3D CAD thickness. So very straightforward. So once we have that single part or single subassembly defined, we can verify the model response at this level before we start to look at the overall assembly definition. So this is one of the unique things about Apex, is that we can quickly perform a subassembly verification. So in the model browser tree, just right click on the subassembly of interest, place in the analysis scene, so that basically sets up the job parameters. So we need to first of all define the material. So we've got an aluminium 7075 definition with elastic modulus, Poisson's ratio, and importantly the mass description or mass definition, because we're going to run in this case a normal modes analysis. So that by default it's set to a static analysis. So we've got an analysis verification flag saying that we've got no loads or boundary conditions. So for normal modes we don't need those, we can just perform a free modal analysis. So run through very quickly, and we can see the analysis response based on the single subassembly that they're interested in. So going into post-processing, and we can see we've got mode 7, which is the first elastic mode for a structure that's tied together properly. We can see the deformed shape. We can look at fringe plots in terms of deformation and or strain energy to allow us to assess what's going on. So we can see here, so turn the fringe plot on and switching to strain energy, and we can see the 7th mode, which is the first elastic mode again, shows a sort of hinging effect where we've got a lack of stiffener in the overall model, and we can cycle through each discrete mode and make sense of the model response. So what Apex does, it uses the concept of computational parts. So based on subassembly verification, we can see this for an example jet engine. Every verification that we do is stored within the assembly architecture and then can be reused for subsequent analysis at the master assembly level, and ultimately that gives us a huge increase in efficiency in terms of the overall way in which we work with the assembly, both verifying at a subassembly level and then effectively merging those assemblies or subassemblies together for the full assembly definition. So we're using that concept in this example. So bringing the full model structure back into play, or into view rather, and again using the element quality index just to show where we've got some elements which have failed the element quality checks. So I think we've got 22 failed elements at this level. So we can just work our way around each particular failed region within the model browser tree, which is showing us, it terms each overextension of the mid-surface as a glob, a term used, and we can look through each one of those globs, as it were, to see, to isolate and enhance for each particular region where we've got poor element quality. So just cycling through the model. I'm going to skip a couple of steps in a moment, but just giving you an indication of how you work on the subassembly and a full assembly definition in terms of element quality, and we can just work our way through. So just jumping a couple of steps there and just tidying up some of the remaining two poor quality regions. And again, these are all just slight extensions of the mid-surfacing operation. We could perhaps tailor some of the mid-surface surfacing operation to work in a slightly cleaner manner, both from a defeaturing and a resultant mid-surfacing definition. But obviously we just hit this model with a quite a broad set of parameters just to show the overall technique that we would use for that definition. So we've isolated, or rather fixed the failed elements. Now we can isolate some of the poor quality regions. So if we look at a couple of these struts, we've got some pretty skewed quad elements, so we're just going to isolate a couple of those struts from view and just operate on those, the single entities, as it were. So we're going to look at some of the sketcher tools. So we're going to create a new part construction, as it were. So any geometry that we use for creation or splitting or manipulation of geometry, and the resultant mesh is going to end up within that construction part. So we're going to sketch tools, and now we're just going to simply sketch on a plane just a simple rectangle which we're going to use for cutting the components on screen. So once we have that geometry defined, just turning the wireframe off, showing us the rendered view, and then we're going to move or transform that cut surface into a position which is normal to the strut representation. So just manipulating some of the transformation tools just to bring the cut surface into the correct position. And we can see it's just a simple drag and drop operation, but so we're not having to define coordinate frames or vectors or anything like that for the movement. It's all done from a mouse manipulation perspective, as it were. So we're going to split those surfaces and modify the underlying mesh definition. So split the surface, split the strut using the cut surface, and we can see the mesh is updated, and then just move that transform object, first of all setting the vector normal to the surface, so we're moving in the correct orientation. Again, very quick to manipulate the handles on these transform tools, or transform and rotate tools for that matter, and then move to the new location where we want to cut the mesh, and again go back into geometry edit tools, split surfaces. So we're going to split the strut surfaces again by the master cut surface, and the mesh is updated. The quality index is updated as well, so we can see in real time the manipulation, or the effect of the manipulation that we've got within the model. So a couple more edits we're going to make. So we're going to split based on a curve rather than a surface. So pick the surface of interest, pick the two ends of the curve, and then middle mouse button to accept. The geometry split, the mesh is updated, and the quality index is updated as well. Again, so just repeating that. So again, sort of standard mantra of Apex, but the direct modeling tools allow us to do very, very fast model edits. One thing that's going on in the background as well is that the shell properties are updated for this strut as we manipulate and modify the structure. So again, you can see there we've got some much improved mesh definition for that, and we can repeat that for the bulk of the structure to give us the mesh definition that we want. Again, just running through this pretty quickly in terms of the demonstration. So once we've got those mesh edits done, we can check the shell thickness definition. So by putting the surfaces on and looking at the 3D representation of shell thickness, just working its way through for this set of property sets. So we can see, yeah, we've got one shell which is very much thicker than the rest of the shells. So looking at that in detail, and we can see there the mid-surfacing operation has mid-surfaced basically a thick solid, which doesn't lend itself well to the shell definition. We could probably get away with it from an analysis perspective, but wouldn't get very good results or stiffness definition or even connection definition at that interface. So just looking at the solid that's defined in the first place, and again turning the hex meshable colours on, so we can see this is green, so it is hex meshable from straight off the bat, as it were. So you can see the resultant mesh definition. So just putting the mesh into wireframe, and then we're going to defeature just to remove some of the holes. So again, manual approach, just pick the solid faces which we want to remove from the overall definition, and again the solid is updated, and the mesh is updated in line with that as well. So again, huge time savings in terms of the overall definition. So we could check the element quality, but looks pretty good to go as it currently stands, and we can we're happy to go with that representation. Okay, so once we've got the full assembly defined from a mesh perspective, so we've got all the thin shells manipulated, quality checked, and properties assigned, and also thick shell for the thicker regions, or hex mesh for the thicker regions, we can now glue the full assembly together. So using the default glue pair tolerance of 5mm, and that looks for entities within that tolerance and glues them together. You may well have seen one of the previous tutorials or webinars where we looked at explicit connector technology, and part of that was focused on the glue, which is effectively an internal MPC definition defined on an MSC Nastran base level. So once we've got those controlled, we can view each glue pair, so a connection between two parts or sub-assemblies, and cycle away through the definition within the model browser tree. One thing I'd say is that the glue technology does consider the extreme fibre surfaces of each shell element. So if you've got two solids butting which are represented as shells, it will glue them together correctly. So once we've got that model definition built, we can look at the full verification and analysis of the structure. So from an assembly level definition, so just place an analysis scene for each, or the full assembly as we require, and we can see analysis readiness has thrown up that we haven't got a material defined, so we can simply assign the aluminium 7075 material across the full structure, and we're now good to go from a normal modes verification run perspective. So we run the analysis, and again, if you remember, I was talking about computational parts earlier. So any parts, any sub-assemblies which we've verified in the background or prior to this point, that structural or matrix definition, if you like, from an FEA perspective, has been stored internally and will speed up the full solve. So if we wanted to, we could go through each discrete part or sub-assembly and verify on their own basis, and then when we bring them together, the analysis time is far increased over a raw analysis, as it were. So again, looking at the elastic mode response, so mode 7 and above, so mode 1 to 6 are rigid body modes with very low frequencies, and so looking at the mode 7 response, and again displacement, we can look at strain energy as well as a further check, but we're pretty happy with that definition. Everything's tied together, and the structure's moving with a clean definition, as we'd expect. So once we've verified the model, we can export the full model definition, and we're turning on the hierarchical export, which basically creates a series of include files which are defined to mirror the sub-assembly architecture. So again, yeah, if you look in detail, and those who are familiar with the Nastran deck definition, but all of those include file definitions are defined in the Apex product structure. So we've got a very close tie-up between the two representations, which can have significant advantages from a Nastran or an MSC Nastran solution perspective. So once we've verified and potentially exported the model, we can integrate the analysis assembly into a larger definition. So in this case, we've got a fuselage skin defined, and we glue the original assembly into the skin definition, and again, the previous webinar, or one of the webinars we've looked at, goes over the glue technology from a mechanics perspective in terms of load transfer, both for force and moment. Defining a pressure condition, so we've got external pressure defined on the model, just skipping over that very quickly, and then running our first true static load case. So we had a constraint in there as well to stop the model flying off into outer space. So running through that, and again, we've got a very thin fuselage, so this is just an example, but it highlights the way the load transfer is moving into the fuselage frame. So taking the fuselage skin assembly out of view and post-processing based purely on the overall original sub-assembly, and we can see by looking at the volumeized stresses and putting in a 200 MPa limit, which might be appropriate for the stress limit that we've got defined for the structure, and we can look at the major response and how the load is being tracked or distributed through the structure. So moving on to model representation within Apex, which allows us to look at models with different fidelities in a single database. So the CAD definition for this particular fuselage frame, and we look in detail and maybe some of the output from the original analysis, we can see we've got a joint of interest. First of all, FE representation 1, course model definition, loads model with a 10 mm edge length and glued contact. We're going to run through that, the setup of the first model representation, and then look at a more detailed joint representation as a second representation, again within the same database. So first of all, we're going to use some of the sketching tools to just cut or chop, for want of a better term, a portion of the original assembly definition out to create a region of interest assembly and control that using whichever means we need to within Apex. So first of all, sketching a surface normal to the cut. So once we've got that, we're basically splitting this surface in a manner which will allow us to cut the overall grey assembly shown on screen now. So if you just bear with me, and the cuts will make sense in a moment. So I'm just cutting, or rather just cutting out the cut plane, the cut surface geometry to allow us to chop the white or grey subassembly. So just using the split surfaces point-to-point option. So once we split those surfaces, we can then delete the surfaces we don't need. So again, just selecting in the viewport and deleting, and we're left with this this profile surface, if you like. So we're now going to push-pull that surface into a 3D form to create a bounding box for the region we're going to cut from the original assembly definition. So using the split tool, we're going to simply highlight the entities. So this will be solids, surfaces, and the underlying shell mesh based on that bounding box definition. So picked all the surfaces in the region of interest, and then highlight the cut surfaces just from the 3D solid, and then middle mouse button to accept. And Apex has made those cuts and updated the assembly architecture, or updated the geometry mesh and underlying assembly architecture to reflect those edits. So once we've got the region cut, we're going to create a new subassembly which we're going to define as our course model representation for the resultant analysis definition. So we're calling this frame 11 region of interest course, and then the reason for doing this will become clearer in a moment. And then we're going to select as a screen pick all of those entities. So we're going to cut and paste them into the model browser tree, and if we change the colour, we can now see that those entities now belong to a different subassembly. So we're going to move those into the overall subassembly. So frame 11 analysis is the master assembly, and underneath that we've got frame 11 idealized shown in grey or white, and then frame 11 region of interest course shown in blue. We're now going to glue the structure together at the interfaces, so just giving us a message saying overwrite or ignore any underlying glue definition. So we're going to ignore those, and then we can look in the browser tree and then rename the glue definitions between the larger white subassembly and the region of interest blue subassembly, and we can look at those glue patch definitions accordingly as well. So once we've got those defined, we can just right click on the overall assembly definition and create a model representation, in this case frame 11 analysis representation course, and we're happy with the structural definition and also the glue contact definition at that level. So we're now going to move on to our second representation. So we want a much more detailed joint model representation at the region of interest. So we're going to have a finer mesh, in this case 3mm edge length, and then we're going to use discrete fasteners to tie things together. So we've made some geometry edits and cuts using the standard Apex functionality, similar to what we've shown in some of the other tutorials or webinars, but we can see now we've got a different fidelity model altogether, and those are the fasteners shown. We've used one of the Python scripts to develop those fasteners very quickly, and we've created the glued contact. So if we look in the model browser tree, so our assembly contains both the coarse model definition and also the fine glue contact definition. So if we just show those in view, and we can see those the glue between the coarse and the fine model representation at this stage. So once we're happy with those, we can go back into the frame 11 analysis subassembly and create a new representation. So this time we're going to call it frame 11 analysis representation fine, and we're going to check off the coarse glue representation, and also the where are we? The frame 11 region of interest coarse. So we've taken out the structure for the coarse model and also the glue for the coarse model. So effectively we've got our model representation, which now does not consider any of the coarse model definition in that local joint region. Again, so we can run the analysis for one or both of those model representations. We've done the runs already, and we can just double click on the study, so the output results, and then post-process for each representation to show the particular model response. So post-processing, first of all, for model representation 1, so this is the coarse 10mm element edge length, which uses glued contact at the interfaces, and we can look at the stress levels developed, taking the skin out of view and setting the extreme stress limit to 200 MPa, and we can see the fringe that's developed at that level. And then we can repeat that, so we can simply double click and change the representation output type to the finer model, and taking the skin out of view, and we can look at the again the von Mises stress, again setting the limit to 200 MPa, so we've got like for like comparison, and we can see the change in overall model response. So again, two different representations contained within the same model architecture. And again, depending on what we're trying to do, whether this is a loads model for screening, understanding load path, or a fine model for understanding detailed joint response and maybe fastener loads, bypass between, or bearing bypass load between fasteners, we've got a good definition of that representation, and Apex is able to handle both model representations in a single representation model. Okay, thanks for watching this tutorial, and I hope you found it both informative and interesting. Be sure to keep an eye out for the remaining tutorials in the 101 series to illustrate how Apex can help with your FEA process.